Okay, do you have any question on anything? Good, by far? Before getting into the details, let's just repeat what we have learned before, by far, and see if we can find out the correct answers. If I power up this op-amp by plus 15 or minus 15, what is VL? Just list the equation. So VL equals what? Minus, because here's 0, here's 0, it's virtually shorted because of the feedback, and what? Remember the interview question? First, so these two, if they are virtually shorted, the requirements are negative feedback and infinite what? AOL is what? Okay, just seal this in your mind, okay? Super important. How did I derive this? I'm going to repeat it. So 0, 0, V in minus 0 over R1 is a current flowing here. Because it's a super high input impedance, it's not getting current inside, so it's going outside and through the feedback resistor and eventually reach the VL. If you have a load, it's going to go through the load, okay? This is RL. So this V in minus 0 over R1 equals 0 minus VL over RF, right? Just moving things around, you're getting V in RF equals minus R1 VO. So that's why VO over V in equals minus RF over R1. That's an inverting configuration. Inverting configuration because the input is going to the inverting terminal. That's why it's called the inverting configuration. Or sometimes it's called inverting amplifier. Another side note here. So this seems like a voltage amplifier because you got a V in, you got a V out with a gain, right? But actually this is a current to voltage converter being used in industry. It's everywhere. You even have it in your pocket right now. So this is called TIA. It's something outside of this scope of this class. But this is a current to voltage converter. Why is the current to voltage converter? Because you can see that it's basically a current going through the resistor and getting amplified by RF. So RF is the current gain. TIA means transimpedance amplifier. It's a basic structure being used to amplify photocurrents. So things like this. If you see a current source directly being injected into the inverting terminal, I have a huge RF, for example. In one of the examples, actually in tutorial 6, shows a current signal instead of voltage signal. If this is like 1 mega, okay, you can add a resistor, but you don't have to because it's not being used. Because you don't need a resistor to convert that voltage into a current. It's already a current. So this structure is a very typical TIA being used in your camera. That's why I'm saying it's everywhere in your pocket. So if you have a photodiode, diode. If a diode receives photon, it's going to convert the photon into a photocurrent. Okay, but the opposite way for LEDs, you inject a current, it's going to emit photons, right? If you use this little diode as a photodiode, it will be able to intake photons and convert into a photocurrent. It's tiny, usually in picoamps, for example, 1 picoamp. Okay, to replace this current source as a model. So what's happening is this current is going to flow through here to ground and creating a voltage, which is called VL. So that's how you get your signal, voltage signal of the cameras. So look at our phone, you have a little CMOS imager in there. Right? So a camera is a chip in your, it's a digital camera, is a chip in your, behind the lens of the camera of the phone, right? So has, for example, 1 million times 1 million pixels, and every single pixel is basically one little photodiode. And that photodiode is connected to a little TIA, which is transimpedance amplifier with op-amp on it. So that photocurrent is being timed, multiplied by this feedback resistor to generate the voltage. So depending on the intensity of the light, you are getting a different voltage. So that voltage is being digitized by the computer system. Eventually, you are getting a digital signal in a matrix, because this is the matrix. So the voltage signal will be put in the matrix and being digitally processed by the computer. So eventually, you are receiving a video or image in your phone. That's how that works. So now, what you need to know is if this is given to you, can you calculate the voltage gain? Right? It's just basically using a current. Ohm's law, get current flow through it. So the thing we need to remember now is these are equal if this is a negative feedback, and I think in all the examples in either tutorial 6 or homework 6, they are all assumed to be ideal op-amps, so which means it has an infinite open loop gain, and you'll force these two pins to be equal to each other. So in that case, 0 volts, 0 volts. That's a conclusion. If you got a 0 volt, you see it's grounded, you know this immediately this is 0 volts. So this is used for every single example in the homework. Make sure you know that, right? I don't think you have any comparators, so they all have negative feedback. So in that case, they are all equal. They're all equal. Okay, then do the Ohm's law. Find out, VL, easy. Another configuration you'll see in tutorial 6, which is due tonight, I think. RF is always negative feedback, no matter where the signal is being injected into. Could be the inverting terminal, could be the non-inverting terminal. So this time, VE is connected to the non-inverting, so the plus. Compared to this guy, VE is over here, across the resistor and connected to inverting. But now it's the second structure. We only have two structures. The second structure, you have the VN being connected to the non-inverting terminal, and this terminal is just getting grounded. And you have plus 15 and minus 15. Let's code R1 here. All right. Is this ideal op-amp? Yes, we always assume it's ideal op-amp. Okay. Is there a negative feedback? Yes, it's negative feedback. Connect V out to the inverting terminal. So negative feedback, no problem. All right. So what's the conclusion? Immediately can draw from this. What's the conclusion? Interview question, right? Just asking in the opposite way. Interview question with TI, okay? They're asking, why the op-amps two terminals are equal? What are the two answers? I'm repeating, right? Negative feedback and infinite open loop gain. Keep that in mind. Very common interview question. Make sure you know that, all right? That's why they are equal. Here. Ideal op-amp, so infinite open loop gain, right? AOL is infinite. Negative feedback, yes. What's the conclusion? What's the conclusion now? They are equal, right? They are equal. So what's the voltage here? V in. Is this voltage given? Is this voltage given? 0 volts. Can you calculate the gain or V out? Yes, of course. So use the same concept. Currents flows this way. We just draw it that way. Doesn't matter. It's negative or positive. Even though you are wondering like why current can flow from ground, it doesn't matter. If there's some current going into ground, there will be some current going out of it. Just a sign issue. Okay, just change the sign. Now let's see. What's the current here? 0 minus V in over what? R1 equals what? The current is not flowing into the op-amp always. Keep that in mind. Because it's super high input impedance. So like a disconnect circuit. It's going out and going through RF. It's V in minus V out over RF. Right? And then minus V in RF equals V in R1 minus V out R1. Right? So V out R1 equals V in RF plus R1. So V out over V in is RF plus R1 over R1, which is 1 plus RF over R1. Something you should be able to answer immediately if you're interviewing these any relevant companies. Okay, so the voltage gain of the inverting amplifier is this, and with the non-inverting amplifier, there's no negative sign, so it's directly it's a positive gain. So there's no phase shift. What does that mean? You have an input signal, and that's the output signal. It's going to be nicely amplified by this gain. What about this one? Negative sign. Input signal, output signal. Make sense? That's the two major things you need to know. And when you are working on the homework assignments, if you are wondering how these were derived, you can always come back. But I believe for most of the cases, you just need to know these two equations. It's beneficial to know how these are derived because sometimes they may vary some of the resistor connections. So, but it's not changing the way you to calculate the gain. It's always getting the current. It's the same current because there's no current getting into it. It's very simple Ohm's law. It's 100 times easier than 70s and Norton's equivalent or all the dependent sources before midterm exam, because exam 1. Any questions on this? I'll show some examples really quick. We'll talk about because all these problems over here these are textbook problems which are not really practical. So that's why they always use dual supplies. So two supplies, which means you have two power supplies, negative voltage and positive voltage, so you can have the signal swing around 0 volts. So we are not adding any. We are not lifting the signal to a certain level. The reason for that is for most of the circuits, we don't have negative voltage provided on the board. So the lowest voltage is just ground, 0 volts. So in that case, just for using the op-amp, then you have to generate the power supply. It's not really practical. So usually we ground it and then we have to lift it. I'm going to show you how that calculation works if you still have time, because I have to give the priority to the tutorial 6, which is due tonight. Okay, let's go through some of the problems first. So if you look at, so I did this for you guys, I think, yesterday on Wednesday. Oh no, on Wednesday, the day before yesterday. Just a very quick review on this. I don't even need to care about the questions, right? Just look at this problem. Is it very simple inverting amplifier? You got a V in here, right? It's a minus sign, so it's an inverting amplifier. This is grounded. There's no difference compared to the one I just drew on the paper, go through. And it's not asking very tricky questions. So, this one, sorry, this one. V in, right? Inverting amplifier, and that's the voltage gain. That's how you derive the voltage gain. So it's asking determine the voltage at the output of op-amp when the circuit operates in saturation. Okay, so this is something I just didn't talk about, but sometimes you'll hear the term here, linear region or saturation. It's because you have the supplies which are 15 to minus 15. That's the range. That's the total range of the supply you can provide to the board. So if you have a voltage input, now let's take a look at this game here. Okay, so 20K divided by 6K, it's roughly like a 3 point something, right? Okay, if you have 4 volts as an input, let's say 6 volts as an input, 6 volts times the 3 times something gain, right? So the VL will be what? At least 18 or above. But the maximum you can provide is 15 to minus 15. So it's going to saturate at 15. So what's going to happen is you're expecting input signal and output signal, right? That's what you're expecting. However, what's going to happen is get your input signal and won't reach that high. So for example, this is 18, okay? And won't reach 18 because it's going to saturate at 15. So what's going to happen is it's going to saturate here, won't show this entire sine wave. You are losing signals because of it's getting saturated at 15. Since the circuit cannot provide anything above 15 or lower than negative 15. So this is what's going to happen. So just know that. So in order to find out the permissible V in, what you can do is just assume you are getting the maximum output. For example, you assume VL to be 15 or negative 15, and then calculate back so you can find out the range for the input, right? That shouldn't be a difficult problem to calculate. And so that input will operate your circuit in the linear region because it's not saturating. That's how it's getting cold. It's a linear region. It's linearly operated. Question on this? Good. This one, see, it's a current source. It's a current source. Now this time it's different, right? It's not a voltage source, so we'll have to use the voltage minus this voltage to get a current because the current is right provided. It's even easier. So current comes in. It goes here or no? No. Super high input impedance is disconnected circuit. So it's going to go up and reach here. You got a current, you got a resistors. It's super simple, right? To calculate the calculate what? Currents or voltages if it's needed, right? And also Vx is given on the other side of the terminal. So is there a negative feedback? Yes. And we're always assuming it's an ideal op-amp, so it's an infinite open loop gain. So what's the conclusion? They are equal. All right. So Vx is given, whatever Vx is 3 volts in here. So what's the voltage here? 3 volts. Basically, you know everything about it. You know everything about it. So one quick question: if you just know the current without knowing the voltage here, can you still calculate everything? Current flows through the resistor, you know the drop, but since there's no reference, so you don't know what exactly the value is over here, since there's no reference. So if the voltage here is given, right, and you get a current, so find out the drop here. Since this is given 3 volts, dropped by whatever here, so you can get VL easily, right? So you can calculate everything here, no problem at all. What about this? What about this? That's the same problem, right? So inverting configuration, got a voltage V in, and it's grounded, 0 volts, negative feedback, and ideal op-amp assumed. So it's infinite open loop gain, 0 volts, 0 volts. So you got 0 volts here, Vs is given, find a current, done. What about this? Let's come back to this problem and revisit this really quick. So it's non-inverting configuration. It's a non-inverting connection because V-in is being connected to the non-inverting terminal. Okay, the voltage connect to here, and because there's a negative feedback, and also the open loop gain is infinity. That's why we know that since this voltage is just connected to the non-inverting but not connecting anywhere else. However, since we know these two, so this is being measured to here. So the voltage here is given as well. If you know this voltage is given, right? If this voltage is given, we know here is 0 volts, and we can calculate the current by Ohm's law. Current goes through RF. We will be able to know our VO, right? You can derive it yourself if you want. Otherwise, just using the conclusion here is also fine. If you just directly want to use it instead of calculating everything through, right? So that's the voltage gain for the non-inverting configuration. And now let's take a look at this. Voltage, resistor, any current. Any current. It's like a voltage, resistor, disconnected, any current. No current. So what's the voltage here? Vx, it's not changing. Negative feedback or no? Negative feedback or no? Or no negative feedback? No negative feedback, right? And also it's ideal, right? It's always ideal. So what's the voltage here? So voltage here? Vx. Can you calculate the current? Yes, 0 volts here, right? It's grounded. Okay? So 0 minus Vx over R1 will be the current here. It's not flowing into the op-amp, it's going up and come back, reach the V out eventually. So can you calculate V out? Because it's connecting to the inverting terminal.
Oh, okay.
Yeah.
So is there no negative feedback when the in is connected to the positive terminal?
If there's no negative feedback, these won't be equal
So there is negative.
because it's connected to the inverting terminal. That's why it's negative feedback. I think we explained that a little bit last time. So why negative feedback works? Why that works? Remember we talked about that a little bit really quick last time. So the op-amp is designed in a way that VL equals VP minus VM times AOL, right? Yeah. This is designed in the circuit. So imagine that if VP is slightly larger than VM, what's going to happen? This will be a little plus, right? A little positive number here. And times like 100 million will give you like 100, even this is only like 1 volt difference. It can be smaller, but let's just use 1 volt, it's easier to calculate. So it's trying to have a surge, voltage surge with a positive number, right? And that voltage will be superimposed to this voltage. Just think about superposition right now. Okay, it will be superimposed to here and bring this up until they are equal. So this becomes 0. So there's no voltage being imposed in here anymore. So it happens really quick. Almost not allowing this to happen, you know? Because electrons can travel at almost the same speed as light, right? Super fast. And because the open loop gain is super high, so the surge happens, the slope of the surge, for example, there's a little surge like this, and the slope is really deep, steep as well, which will help bringing these two terminals to be equal really quickly. This is not even happening, but it's just, you know, keeping these two terminals to be equal. And you are wondering, and if they're equal, so 0 volts, right? If you got a 0 volts here, why the input is impacting this point? confused, right? Super confusing. How that happens? Like you asked a question last time, it's also a very good question. If there's no current getting into the op-amp, why do we still need it? All good questions to ask ourselves. Let's go through that again one more time. Let's do this first. Answer this question first, okay? So we remove. Let's see. We remove that little triangle here. So it's gone. Okay, it's gone. Nothing. You got RF. You got R1. You got a V in. Are you able to amplify V in at all through this circuit without the op-amp? No. Why? Because being dropped twice. It's being dropped twice by the resistor. It's a voltage divider. There's no way that we can amplify this signal at all. It's being divided. So why the op-amp is playing a role here? Why the op-amp is playing a role here? If you look at it, why it's playing a role here? Because it's virtually short this point because of the negative feedback and infinite open loop gain. I'm not writing this anymore. So because of the negative feedback, like the mechanism I just described over here really quick, because of that super high open loop gain and the negative feedback, you are able to force these 2 points to be almost equal to each other. So in that case, you can drop V in very quickly to 0, somewhere really close to 0, and then keep dropping it, to a negative voltage after the 0 point, and eventually you are reaching a voltage amplitude which is larger. It's getting amplified, but it's a negative voltage. As I said, RF over R1 minus, right? So when we look at the voltage, if it's a big voltage, it's a large voltage, it's comparing to ground, even though it has a negative sign in front of it, but the amplitude is higher than 0, right? So 0 is just 0. 0 is a low voltage. We're looking at absolute value, not the negative sign, right? So a negative large voltage like this, it is a large voltage. If you inject the voltage into a speaker, it's going to make a sound. Okay, it's not a small voltage. So compared to this one, it's being amplified to here. It's being amplified, even though there's a phase shift or something. But this one doesn't even have a phase shift. But you are getting a stronger voltage here, even though it's negative. That's why when we force it to ground really quickly, by doing that, by just drop it to no voltage at all, very quickly, then we can use whatever the voltage, the resistor setting over here to multiply by the current to give you a higher voltage. That's how it's getting amplified, because the op-amp is forcing this one to ground, to a virtual ground, right? Then we brought another question. So why not just simply in this circuit just ground here, just ground it? Why do we have to create a virtual ground instead of just ground it? Yeah, if you really physically ground it, that's the real physical ground. What's going to happen is it's going to circle the current to itself instead of going to V out. Virtual ground is not a real ground. It's just 0 volts, but it's not physically wired to the cathode of the battery. Does that make sense? That's a fundamental value of the op-amp. Right? That's how a signal is getting amplified. I know it's confusing. I know. But just for this problem, Vx is over here. We know Vx is here, so we are able to find out V out. This is a non-inverting terminal. Just looking at Vx, right? Input voltage is being injected into the non-inverting terminal here instead of the inverting terminal. Any questions on this by far? So you won't have any problems if you know that these two are equal. That's it. If you know that these are equal, everything else is just the first week's problem in this course. Ohm's law, that's it. Voltage divided by current, you got a resistance. Voltage divided by resistance, you got a current. That's it. Very simple problem. Just ignore that triangle. I know, hate it, but just ignore it. Okay. What about this? What's that?
So since there's no change when you're virtually grounding it, why does it like sine wave back up? It just continues going, right? Shouldn't,
This one?
yeah, in the like situation, it wouldn't be the like graph would be and just keep dropping if there's no change in the virtual ground. Why does it go back up? Maybe I'm thinking that's very wrong.
Oh, because of the calculation. Remember we calculated just using Ohm's law. Why it comes back? Because the current is not getting into it. Because the device blocked any current getting into it, so the current has no other place to go. It has to go this way. That's another good thing I want to talk about really quick. Right. So, for example, you are getting a sine wave here, right? Okay, keep that in mind. This is a really interesting thing to think about. I was thinking about this yesterday when I was running in the morning, and how should I explain this to you guys? So, look at this. I could inject a sine wave as V in, right? And eventually I got to amplify V out. Makes sense, right? That's why we want to use op-amps. So, if sine wave is being injected in here, are you getting a little AC here as well, a sine wave, or no? Why? Keep that in mind. That's important. Are you getting anything here? It just crossed the resistor. You lost all the sine wave. Why? Why is it? Yeah, because 0 is a DC 0. I told you it's 0 volts. It's going to be 0 volts. The sine wave is not being added to it because it's grounded. Does that make sense? So now let's see this. But do you still have current flowing here? You still have current, right? The current and voltage are different things. You still have current, but you don't have a voltage here. So look at this example. It's very similar. 5 volts, ground here, right? Same thing. What's the voltage here? 0. It's grounded. It's going to be always 0. You are not getting a sine wave. You are not getting anything there. If you probe it, want to probe the voltage. However, if you inject a sine wave here, what's going to happen? Are you having a sine wave here? It's grounded. Okay? Which means you are not, if you probe it, you are not having any voltage. It's going to be 0, absolutely 0 volts. But do you have current? You have current. You still have current going through it. You just ground this point as a reference voltage. What's that?
And so, going back to this question, like, it comes back up because the changing voltage changes the current, so when the current's amplified,
Yeah, the current is getting amplified. That's right. Yeah.
Oh, so the amplified sine wave is what we're seeing from current.
Yeah, the currents are getting amplified. Mm-hmm. Because it's immediately converting that voltage to current. So it's actually current going through it.
So the voltage out will be constant voltage, but the current will change.
The voltage is 0 volts here, and V in here, and V out here.
And if V in's a sine wave,
V in could be a sine wave, could be a DC voltage, doesn't matter.
would V out also be a sine wave?
V out, yeah, if V in is a sine wave, V out will be a sine wave, but inverted. Okay? For the non-inverting, it's very similar. V in here, it could be a sine wave, could be a DC voltage, doesn't matter. It will be measured to this point. Because given, right? I told you. Negative feedback, infinite open loop gain. So they are equal. So whatever happening here is going to happen here as well. Sine wave, DC, doesn't matter, just add to it. Alright? Okay? Do you have any sine wave here? No, if you probe it, it's gonna be 0. Just 0, nothing. Another circuit to look at. Summing circuit. This could be confusing if I don't explain this. You're like, it's okay, everything's confusing. Don't worry about that, Dr. Lee. Alright, let's see this. Look at this. I think whoever designs this problem didn't explain that really well in the problem. So let me explain that over here for you guys. It's asking you that if these two are off, if these are just voltages, right? Voltages. Batteries. Batteries. If these two are off, does that mean that you have disconnect circuit or it's shorted to ground? Gotta be clear. No, it's actually not. It should be shorted actually, but it's not. It's telling you that they are disconnected. It's a floating wire. It's not doing anything. No current. So what you have to do is ignore it. It's gone. It's specifically just the one problem in tutorial 6. Okay, keep that in mind. This one. Keep that in mind. No current. Okay. So let's don't get into that specific problem. However, if you just assume that they exist, V1, V2, V3 exist. How to find out V out? Is that something easy to do? Negative feedback or no? Yes. Ideal or no? Yes. Equal or no? Yes. 0, 0, right? Okay? Just use KCL. KCL. This is the node you want to look at. Okay? So current going out. I got 3 current injecting into that node. So you are getting V1 minus 0 over R1, right? That's 1 branch current plus V2 minus 0 over R2, that's the second branch current, and plus V3 minus 0 over R3, that's the 3 branch currents getting into the node and equals the current flowing out from the node, which is 0 minus VL over R, it's called RB there. That's it. If it's asking you to assume that V2 and V3 are off, which means you want to ignore these two or giving a 0 to these voltages. You don't even want to use it. Just don't give a 0. Give a 0 is grounded. Just don't even give anything to it. I think that's the only thing you need to use. All right? Make sense? It's unclear here because it's just telling you it's off. What does that off mean? Grounded or just disconnected? It's going to be different results. Any question on this? Still the same problem, right? Very similar. And there's the last one, last example. You have to know how that works. It's called difference amplifier. It's eventually it gives you something practical in the real world. So this is called difference amplifier. Or sometimes you'll see it's a differential amplifier. It's the same thing. Okay. Differential amplifier, because amplifying the difference between these two nodes. how do we calculate the voltage gain of this guy? Keep that in mind. Have to keep it symmetrical, and that's critical because it's very sensitive to noise. I don't have time to derive it today, but keep that in mind. They have to be symmetrical. R2 equals R2. That's why I label the same resistor. R1 equals R1. And when you are doing the layout on the circuit board, you don't want to just directly connect it randomly. You have to look at the distance of the wires to keep the distance from the source and the resistor to the op-amp to be the same to reduce the noise. What's that?
So the two R1s and two R2s are different resistors, it's at the same value?
Yes.
Okay.
Yes, that's right. Keep it symmetrical, important. Where to get started? I want to know the gain, right? Why do I need to know the gain? That's how you design the amplifier circuit. You know the circuit, you know the signal is like 100 millivolts, right? And your ADC, analog to digital converter, accept the range of 0 to 5. Okay, so you want to amplify your signal to this range so you can use the resolution. You're not losing any resolution. So from here to here, it's about 50 times, right? Some estimates. So that's why you need to know the resistors to find out the gain of it. That's a process of designing a op-amp circuit. Since right now you're targeting this value, right? Okay. Any current in here. What's the voltage here? No, you got a voltage source. It's a voltage divider. VI2 times what? R2 over what? R1 plus R2. That's the voltage here, right? What's this showing you? Negative feedback. What's the open loop gain? Infinity. Are they equal? Yes. So this guy is also the voltage here. What's the next step? Just find out the current, right? It's the same calculation. Over and over again. VI1 what? Minus this guy. Divided by what? R1 equals the current flowing that way. Okay? Then do this. VI1 times R2 minus VI2 R2 square R1 plus R2 equals VI2 R1 R2 R1 plus R2 minus VL R1. Move all the VIs to the left or to the right and leave this one to the left. So VOR1 equals VI2 R1 R2 over R1 plus R2, this guy, minus VI1 R2 plus VI2 R2 square over R1 plus R2. And next, V out equals VI2 divided by R1 on both sides of the equation. We are having R2 left on top, R1 plus R2, minus VI1 R2 over R1 plus VI2 R2 square R1 plus R2 combine these two. You're getting VI2 R2. Factor this out. 1 plus and this becomes So good to see this. Cancelled. So nice because it's not even getting inverted. Symmetrical, high gain, low noise, nice and sweet. Signal is not even being inverted, no phase shift, with a nice gain over here. So if I have two signals injecting into it, you can say, hey, I just want to ground it. I just want to ground it, which is okay. Which is okay. If you ground it, oh, did I use V2 minus? Oh, if you ground this guy, if you ground the other guy, right? So you're getting 0, so V2 minus 0. So it's amplifying V2, VI2 directly, and without anything getting inverted. That's a really practical amplifier circuit. So this one is being used for this problem. Differential and difference amplifier. Look at it, see if this is the same thing. R2, R2, R1, R1, 2 voltages. What's the voltage? What's the V out here? Vx minus Vy, then what? R2 over R1, that's it. It's 100 times easier than 7 is equivalent, right?
Why were you able to just ground V on one?
Because sometimes the signal is a differential signal. So for example, the input could be, let me draw it for you. So in the real world, what you may see is this. As a differential amplifier, right? Or difference amplifier. R2, R2, R1, R1, V out. So what's happening is you just connect your sensor over here. As the voltage difference is getting amplified. Okay? 2 more minutes. I don't think there's. What about this one? Same circuit, right? Okay, so I think we'll derive the ones with. Oh, we have to go through homework 6 on Monday. Is that due Monday or due Wednesday? I forgot. Homework 6. You probably don't even know. That's okay. You still have time. Okay? But you are good on tutorial 6 now. Alright, we'll see you on Monday.